Okay, so welcome everyone to the first meetup of the part 2 study group for Fast.ai course. And if this is the first time you're joining, our approach is sort of to discuss the lectures followed by some general Q&A among ourselves, followed by a few mini presentations. So today we have the first lecture discussion, which I'll be covering. And followed by that, we have three mini presentations for today. I'll be covering the sequence to sequence paper, sequence to sequence neural translation paper, followed by another paper discussion by Philip. And I believe Robert will be discussing parallel translation, parallel computing using Fast.ai.parallel. So there's this module in Fast.ai that allows you to run parallel computation on your CPU, and it'll be based on that. So if you've had the chance to watch the first lecture, these are the sort of topics that Jeremy has mentioned we'll be covering. And also a quick note that many of this are still at the very cutting edge. For example, object detection, sequence to sequence, attention, transformer, etc. So he's mentioned that these few might be a bit of challenging projects to take on. And this course is sort of designed to keep us busy until the next course, which is around October-ish. So please take your time with these, and I suppose it'll have a built-up speed as we progress with the lectures. We'll also cover, I believe, JIT in the furthermore lectures, which is how PyTorch compiles the code we type inside of it, which is another thing that I'm excited about. And also for all the questions related to Swift for TensorFlow. So we'll be following this bottom-up style for this part 2. And Swift for TensorFlow will just cover the last 2 lectures. So those will be taken by Chris Latner, who is the designer of Swift language. And there was a mention of the pros and cons of both PyTorch and Swift for TensorFlow stacked against each other's. And it was clearly mentioned that the Fast.ai team is still sort of pro Python and pro PyTorch. So that's the direction moving forward. But they're excited about Swift for TensorFlow as maybe a future potential replacement, in the sense that Swift is great in terms of its numerical computation. And the issue with that is there's a very minimal ecosystem around it, and the libraries are not as developed. But if that's something that you're excited about, and if you want to jump in on the early days of development, you might want to take up the last 2 lectures pretty seriously. But the first 5 lectures will just cover PyTorch. And Jeremy has mentioned this game that we'll be playing. I'm sorry, it's slightly crowded, but the end goal is to recreate Fast.ai. And the bottom sort of blocks are what we're allowed to use. The end goal is to replicate most of the portions of PyTorch, the ones mentioned here at least, torch.nn, torch.optim, and recreate Fast.ai. We're allowed to use Python. We're allowed to use standard libraries of Python. We're allowed to use non-data science modules. So that excludes pandas, numpy, and the sister libraries. But we're allowed to use PyTorch for array generation and PyTorch's helper function. We're allowed to use Fast.ai datasets, and we're allowed to use matplotlib while doing this experiment to recreate Fast.ai. And again, blogging is highly encouraged for part 2. So if that's something that you're excited about, or if you want to run your own experiments, those are again highly encouraged for this part. And these are the complete topics that I believe we'll be able to re-implement once we're through with this part. To be honest, I am not familiar with all of them. I'd say at least 40–50% of them did ring some bell, but I'm still not completely thorough with all of them. So even if you cannot recall all of them, that's, I would say, fine. So the target for the first lecture is to teach us how to get started with fitting the model. And there are just 2 steps to it. First, you want to overfit, and then you want to reduce overfitting. That's how Jeremy has mentioned it. And there's some discussion around what is overfitting exactly. So in case you're not particularly clear about it, I'm happy to discuss that. But to give you the gist of it, overfitting is not just the case when your training loss is lesser than your validation loss. That is expected. But it's the case when your accuracy improves, it plateaus, and then sorts of it starts to get worse with your epochs. So that was the mentioned method of, that's what overfitting is defined as in the lecture. These are the 5 steps to avoid overfitting. And it was mentioned that although we take the inverse approach, like reduce the architectural complexity, the other approach should be taken in general. So you should be focusing on other things rather than straight ahead going to your architecture first. And there were 3 papers mentioned in this lecture. I'll share the link again if you've missed them. I did try to read through the initialization one, the one where the authors have mentioned Fixup initialization. It was a bit too math heavy for me. I was able to understand the gist of it, but in case anyone has any thoughts around that, I'll be happy to discuss those also after this presentation. So this is, I believe, the target for the first few lectures, and we're sort of near the 5th block, so to speak. So in any approach to create a CNN model, these are the few steps we take. We perform matrix multiplication, followed by Rayleigh, followed by fully connected forward pass, followed by a backward pass. These are the 4 steps that were covered in the first lecture. And the next ones, Jeremy has mentioned, will be covered in the second lecture itself. So I'll be going over these notebooks related to these 4 parts. And what I'll do instead is I'll do a quick run through of the notebooks, because otherwise I'll essentially be replicating the lecture. But in case you have any questions so far, please let me know.
There is some discussion on overfitting on the chat.
Okay. Did I get it right, or?
Yeah, I think so. I think the thing is that overfitting is not, it's not a thing that where you can say, okay, at this point it is exactly overfitting, and at this point it is not overfitting. So it's kind of a continuous thing that you can assess for a model.
Right.
I mean, you kind of have to decide at one point if you're overfitting or not, but
but it's again relative, I believe.
Yeah.
Okay, so the cool tool that was mentioned, I apologize for these few extra printouts in here, but this cool tool was mentioned in Fast.ai, where they highlighted that the complete library was developed in side of Jupyter notebooks, which to some of you might have sounded a bit wild, but I found it cool because I'm mostly used to Jupyter notebooks over any other IDE. So how that works is you mark your cells with hash export. And I believe this might have been Jeremy's approaches, where he would have experimented inside of a notebook, and whatever cells at the end he concluded would have been useful for the library would have been marked with a hash export, and the script called notebook to script.py, which would convert it essentially into a .py file. And it took Sylvian to about 3 hours to concatenate all of these into the Fast.ai library. So that's how I believe the Fast.ai library was created. In case you're interested, it's inside of the repository. You have to install this library called Fire, which is basically a helper library that allows you to run programs using CLI. So the first block in the presentation, if you remember, was matrix multiplication. And the goal of this notebook, as far as I was able to understand, was to first of all show us how slow Python is really in the wild. And then we sort of slowly implement towards a faster implementation, getting as close to PyTorch as possible, followed by which we implement a complete fully connected forward neural network. And since this is the crux, that's why we need to understand matrix multiplication first. The first thing mentioned was doing testing inside of notebooks. So this function called test was defined where we compare the arguments. And you can run this on possibly any data type out there. So wherever you require to check if the two parameters are equal. And this will be useful when we're trying to perform matrix multiplication to check for ourselves if the output is what we desire it to be. Hence, this was the first test for us defined. It's a unit test in essence. After that, we download the MNIST dataset, and to open it with gzip, it'll be pickle loaded because it's saved as a pickle file. The encoding is Latin one, so that you don't have to guess it randomly. Otherwise, you'll have to follow that weird process. Next, we map all of the training and validation splits as tensors into the following variable names. We do the assertions. If you're familiar with MNIST, these are the assertions that are there. There are 50,000 examples. The shape of the image is 28 by 28. And the basically bitmaps of numbers from 0 to 9. So we verify that. We do a quick sanity check by printing out the image. And followed by that, we initialize our weights. This is, I believe, called Kaiming-Her initialization. So we divide by the square root of the input size, followed by which we define our bias. Now, if you're from a CS background, the simplest matrix multiplication you can think of is going through each element by element inside of the matrices, which would take 3 loops, which accounts to big O of n to the power 3 in itself is a bad practice, I would say. If you're not familiar with big O of n, it's basically a notation how you assess your algorithms. So this is the base algorithm that we sort of try to improve upon. It's a Python baseline, which Jeremy improves by up to 50,000 times in the runtime. So we take 5 examples. Do a simple matrix multiplication by looping over all of the rows followed by columns, and then doing a matrix multiplication operation, which was shared as a song row by column, row by column. So in case you're not familiar with what's going on, each element of each row is being multiplied by the column and being added and stored as a new, I would say, number in the target array or target matrix. Followed by which we are introduced to element-wise operations, which will help us speed up a bit furthermore. Now, if you remember, we had 3 loops above. So Jeremy introduces Frobenius norm, which is represented as follows in programming language. Now this cuts it down to 2 loops. Also, if we can index into the matrix, which is done by putting a simple colon. So what we're doing here is we're broadcasting the array operations row by column essentially and summing them over. So that helps us remove the third loop from the above function. And this in theory brings down the complexity from O of n cubed to O of n to the power 2. And that brings us a speed up of about 170 times, if I remember correctly. I'm sorry if I have deleted the cell from this notebook. But that, even in theory and even in practice, brings us some speed over. And this unit test, so we call torch.allClose. The reason we do this is, since we're using float variables inside of it, floats can vary a bit and they'll actually never be exactly equal. So you need to define this function using allClose, which basically checks if it's within a certain range of tolerance. So it's nearly equal in that sense. Furthermore, we're introduced with broadcasting, which is basically taking one scalar or matrix which might be equal dimension as the other matrix or tensor and broadcasting it to the complete tensor or matrix. So you can add one to, let's say, a row matrix or row tensor, and you can also multiply all of the elements of this tensor by 2, and behind the scenes this gets broadcasted to all of the elements. This will again in the next step help us cut down the runtime furthermore. There are more examples of it. I'm just skipping over them because those are really covered in the lesson. If you want to check how broadcasting is done, there's this function inside of PyTorch, if I remember correctly, which is expand as M. So if you want to see how C tensor gets broadcasted to the M tensor, you can expand it as your target tensor using this function. And yeah.
People on the chat are talking a little bit about why broadcasting makes things faster.
What I was able to make out is because of NumPy or how it's implemented, it's faster under the hood.
Yeah, well, I think one of the points is that things are done in parallel when you do broadcasting, or can be done in parallel. I mean, I'm not a software engineer at this level, so I can't really say it. But I think it's all about one point is loading the data into the cache for processing. So you have to only do it once, and also processing it in parallel, I think. And I mean, GPUs are that much faster because they can do much bigger
broadcasting.
So much bigger bigger matrices or tensors.
Yeah, and I think he did mention that this was derived from some internal broadcasting loops that happened in the traditional languages.
Yeah, I mean, if anyone here is on the line who does know something about this kind of deep C-level stuff, then please jump in, unmute yourself, and explain how broadcasting is so much faster.
So, yeah, go ahead.
Yeah, so the way broadcasted matrix is stored as a single vector that allows us to perform a SIMD operation under the hood in C or a similar language that implements this. So what happens, you are able to pass a larger matrix as a single vector in a single instruction. So that is stored in memory. So disk reads are reduced per se, and hence there is a performance improvement.
The IO read time gets cut down because it's getting stored. That's it.
Because of SIMD, so we can read about SIMD to understand the intricacies.
That's a single input.
Single instruction, multiple data.
Multiple data. So essentially parallelizing it using processor or GPU, whatever you're using.
Yeah.
One of the things also is that when you're doing this broadcasting, the operation happens in C, not in Python. So that's also one of the reasons it happens faster, apart from the previous thing that he was mentioning.
I'm not sure if, okay, we are actually using PyTorch here because these have been mapped to tensors. So I assume this would again be implemented in C.
Yeah, I think there are really different levels. Like when you use PyTorch, you have the Python, which is basically, it's the next thing after a graphical user interface. You really just call functions that are, in this case, then written in CUDA. And even CUDA is using lower level libraries like cuBLAS and stuff that take care of this, deep level stuff.
Okay.
Just one quick question. Like, my understanding was that the first, like, it doesn't go through a loop, so there is no sequence operation as Kai said. It's just sending a burst of digits and they multiply together in a parallel. That was my understanding. However, I have one question with regard to the PyTorch versus a NumPy. Would there be any difference in speed as such if we implement the same broadcasting in NumPy only?
Well,
I don't think there should.
Yeah, go ahead.
I was going to say, I don't think there should be as long as you're using the CPU.
Yes, I would agree to that.
NumPy does not support the GPU, so in that case, you might have a speed up. Assuming your GPU is faster than whatever CPU you have.
Yeah, if you pass the tensor to .CUDA, it will speed it up because it'll be able to leverage the GPU. But if you don't pass the tensor to .CUDA, I would expect NumPy and PyTorch matrix multiplication to be extremely similar.
Yeah.
Okay.
Okay, so I'll move on with the walkthrough. Followed by that, we introduced to this unsqueeze function. Now, if you've followed along, how do you create extra access by passing on none? This is an exaggeration of that, so it's just to help us understand how this does it in the background. So when you do unsqueeze -1, it sort of flips the axes. For this, it converts M into a tensor. So far we managed to cut down again another loop, bringing down the theoretical complexity or even the runtime furthermore. In Bender unsqueeze that was left as a homework to us. I was able to understand the down on paper. If you have any questions, please feel free to discuss them. And this does pass our test of test near, so it does do matrix multiplication correctly. Followed by that, we introduced to Einstein summation, which is also, from what I understood, is again fast. But Jeremy was not very appreciative of this in the sense that we're writing again something inside of a string which is being used to multiply two tensors. So this is just a notation where you mention the first matrix dimension followed by the second matrix dimension, which gets mapped to your target matrix dimension. So that's how it's being written. And if you know the multiplication, the other two dimensions or the internal two numbers of the source matrices should match. So that's understanding Einstein summation. And this is again ridiculously fast, is what I was able to take away from this. Finally, we get to PyTorch, which is about 50,000 faster. So we just do matmul, m1.matmul2, which calls a PyTorch function. And this is the fastest to which we were able to get. And this is almost comparable to einsum, which was sort of implemented by us, but again, Jeremy was not at all appreciative of this. And also, personally, I'm not sure how would you generalize this really well, since this is happening inside of a string. So when you're working on a big neural net, how would you write this into the functions that are going on inside of your loops, whatever? I'll move on to the network notebook if there are no questions from this one.
One of the questions I wanted to ask Sanyam is, when I was running this notebook, I did not exactly the same kind of timings that Jeremy had shown in his own notebook, right? Sometimes, for example, if it is not 50,000 times fast, for example, it came to only say 30,000 times or 20,000 times faster. So did anybody else also have the same kind of experience at the very end when you do the m1.map2mul m2?
I was pretty proud of the fact that I was getting better numbers even in this. So my machine is assumably faster than his. But these values did match for me.
Okay.
It probably depends on the processor.
Okay. Maybe. And also on the background processes. So if you had something going on in the background. That
I
might
was
help.
using, this was the only thing running. I was using a P100 on a GCP, and the numbers, of course, sometimes it came to this number, but most of the times it was a lot less.
Okay. I did get better or worse, plus minus 10%, I would say, but not off by that much.
Okay.
So the next step in building a neural net is sort of implementing a fully connected neural net where we do a forward pass followed by a backward pass. We're not going to be doing the training loop today. We're just going to make sure our input can be passed through the neural net and we can get the losses back from it. That's what this notebook is going to cover. And another quick note, so when I was trying to do this on dogs and cats, normalize was done just for one channel because MNIST is simply black and white. But later on, after struggling with it, I realized I had to normalize the 3 channels and I had to account for the 3 channels of RGB that are there. So hopefully you don't take that pitfall. And there was another quite a bit of discussion around why you want to normalize your validation set similarly to your training set. So you would want to make sure that both of them are normalized in the same manner. If you're normalizing your validation set using just the validation statistics, so that would cause a problem for you in the sense that you really for it as a test set because it's really a proxy to your real world data. So you would want to normalize it with whatever stats you're preparing your own training set with. So the example used was if you normalize red frogs, considering them to be red frogs, and you've trained your model on green frogs, your model in the real world would fail pretty bad because it'll again normalize your red frogs to whatever your neural net already knows. In the sense that it'll normalize green frogs to something that your neural net is learning and brings red frogs to the same level. So please normalize your validations set using the statistics of your training set. Now, our goal with normalization is we want to bring down the mean to 0 and the standard deviation to as close as 1 as possible. Why would we want to do that is to avoid exploding gradients or vanishing gradients. So with deep neural nets, as you go deeper, you'll encounter this problem of, I'm not sure which one of the two was it, exploding gradients or vanishing gradients, where your weights would essentially sum up to infinity or just sum down to 0, both of which you would want to avoid. The first one would be to just use the mean and standard deviation by calling the functions, followed by which we define our architecture. So it has 50 hidden layers and it's a 2-layer fully connected neural network. This is known as chiming, a simplified version of chiming her initialization. So we divide by the square root of the input dimension to your matrix. Again, we assert if the mean and standard deviation are to avoid the problem I had just mentioned.
Satyam?
Yeah.
Just a quick interruption. There is some talk on the chat about why this is faster than NumPy. And I think he's not really using NumPy. So he's doing this for loops through the matrices, and he is doing all the calculations in standard Python, and he's not using the matrix multiplication functions from NumPy. And I think when you would do that, it would be as fast as using PyTorch with CPU. So I think at the beginning of the course video, he said that he's not going to use the NumPy matrix multiplication stuff, only for storing the matrices.
Yeah, what I remember, it was against the rules of the game. So we're only using torch.tensor is the only library that's getting imported.
Yeah.
I'll move it. We define ReLU functions followed by a linear pass. And in I really appreciated is this is how I would initially go about initializing every, and then Jeremy shows us how can we refactor this, followed by another round of refactoring, which really made sense to me. And he did tell us that this is how it's implemented inside of PyTorch. So what we're discussing is how these functions are implemented inside of, I believe, PyTorch. I haven't verified it, but I'm taking him for his word. Another thing that was mentioned in the Kaiming He paper was because they were the first to use Rayleigh, you would have to include this 2 while taking the standard deviation. So 2 divided by this square root of your inputs. That was this neat trick to making sure that your standard deviation is in order, which is what was shown here, that it's not as we expect it to be. Because when we include a Rayleigh, we delete whatever negative values are there. And that can be fixed for the mean by subtracting 0.5 from it, because what we've done is we moved the graph 0.5 above the y-axis. But for standard deviation, you need to include this 2. So that is done after this for the first matrix of weights, followed by which we call the linear from torch.nn, and we check the shapes. Next, we call init.timing, and we call the fan out. So PyTorch by default takes care of fan out, which is depending if you're passing your weights in a forward pass or if you're passing your loss backwards, you need to set this accordingly. And I was digging through the source code. I believe this is taken care of by the callbacks. There was this great talk from Sylvian. I shared it in the Slack channel. Be sure to go through that if you want to understand callbacks. But I believe callbacks accounts for this. Followed by the pass, we call Rayleigh. And again, we check the standard deviation and mean. We really want to make sure that these are done correctly. As a paper highlighted by Jeremy mentions, that if you can just take care of normalizing everything in order, you can even train 10,000 layer deep neural nets with ease without doing extensive regularization and fancy stuff. So that's why the mean and standard deviation are heavily emphasized in this lecture. And we account for that 0.5 shift by subtracting 0.5 from our initially defined Rayleigh. Next, we initialize the weights as discussed earlier with the 2 point defined in the square root. So while replicating, I missed this decimal, which converts it into a float. So just be careful to put the point here. After computing our first set of weights, we pass it through a Rayleigh. We again do our sanity check of mean and standard deviation. These will never be exactly 0 or 1, but these are good enough values in that sense. Finally, we concatenate all of this into a model, which is our first definition of a fully connected forward model. And we check the time performance of the same. We check if those shapes are in order. They are. So as long as you do not see a dump after these assert functions, even if you just copy pasting, you're doing okay. If something is out of order, you'll get a error dump. Next, we define a loss function, which does not make sense here because we're predicting categories, but MSE is for regression. But it's just to keep things simple. So in case it does not make sense to you, please feel free to ignore. We just want to have a placeholder loss function for now. We compute the loss values, which is how off are our predictions, our actual values from how off are our predictions from the real values. That's how MSE works. Next, we define how the gradients are calculated and how the backward pass is done. Now, if you were like me and you had just used PyTorch earlier, this was really easy to just turn on AutoGrad and you can just compute the backward pass easily. But if you really want to understand how that goes on behind the scenes, is you can replicate this notebook by hand, and you'll have a much better understanding speaking from experience. So we define all of the backward passes, and we finally define this forward and backward pass, which will account for both of those. What we're trying to do is we're trying to make sure that our weights and the gradients are calculated correctly. So we clone these into placeholders for verification. And then what we do is we enable requires grad to true, which allows PyTorch to compute the gradients. Then later on, we do compute these and do a quick sanity check that they are indeed near to each other.
I have a question, Sanyam. Could you go up? Could you maybe highlight a little bit more about what's this forward pass and a backward pass? Is it? Could you explain a little bit more what we are trying to achieve or what we are trying to do here? Is it a back propagation we are talking here?
It's a single backprop that is done by hand, and we manually check if these values are equal to what PyTorch computes internally.
So the
And
forward
Jeremy
pass, yeah, sorry, go ahead. So the forward pass is nothing but the multiplication that takes place, like the linear multiplication, then the Rayleigh activation, then the linear activation after that. So that's the forward pass. The backward pass is the backward propagation of the output that you get, so that you adjust it for the gradients, thereby you're able to get the better value of the weights and the parameters that are required as the next forward pass happens, right? So that's the backward pass of the process.
Okay, so once we have done the one pass forward and a backward, are we going to like then check the weights? What we're gonna achieve once we have done the full cycle?
We do not get past that point in this lecture. We just check that for our own sanity that this is similar to what PyTorch does, is because we assume that PyTorch does it correctly. That's why we check it.
Okay.
Correctly.
So to answer your question, that actually is done with the loss parameter, right? So basically, when you do the forward and backward pass, you're optimizing it for the loss, so that the loss is as minimum as it can get. So the whole thing happens so that you get a minimum value of the loss, and when it happens to get into the minimum value, that's when the process starts, or when it starts at the end of the epoch that you give it.
Okay.
You just have to pass it to the training loop. This whole thing. Forward passing, backward, put it in a loop, and it will be a ready network.
Yeah, that's the point where we stop. So I think first thing we discuss in the next lecture is training loops, and how do we adjust the weights according to these losses and gradients.
Okay, and with regard to that He initialization, we are saying that once we achieve the standard deviation of 1 and a mean of a 0, we don't need to do any regularization or like a drop route, weight decay. We we believe that once we have done this, that's like near perfect solution, or what's the outcome?
I apologize, I did not mention it or cite it correctly. There's a different paper which highlights that if you can initialize, it's called Fixup initialization. So if you do that correctly, you can even train 10,000 layer deep neural networks correctly. And this is another paper where they teach us this trick of how do you normalize when you have ReLU networks going on.
And they call it as P-ReLU, I think, prometric ReLU.
I'm not sure about that, but
they call it parameterized, so that instead of having the negative part as 0, there will be a parameter that you can tune.
Yeah, parameterized. Yeah. Okay. Thanks.
No problem. Finally, we get to check if our gradients are in order, which they are. So to do this in PyTorch is pretty easy. You just enable requires grad.true, and you do the forward and backward pass for the same. be careful when you're replicating with the hand. I did not mention dot grad and I was scratching my head for hours. So gradients in torch tensors are stored inside of dot grad. And you check these with your cloned gradients that we had calculated manually. These ones, they are in order. Followed by which we refactor this into a single class. So we define the calls, we pass on the input to the ReLU, and then we subtract the negatives from our original definition just to fix the mean values, followed by which we define the backward pass. Then we define the class linear, where we'll eventually call ReLU. So we do the forward pass, I believe, in the call function, and the backward is called inside of backward function. I'm skipping over this because you just need to ensure that your matrix dimensions are in order to be able to understand this, but please feel free to ask me anything. Finally, we get to compute our gradients, and we define another class, mean squared error. So this is really understanding how can you use classes in Python and really automate this by defining a lot of functions for all of your use cases potentially. Then finally, all of these mini classes will be imported to model class, where we will again call most of the functions that we've defined earlier as helper functions. And this eventually gets to a speed as good as PyTorch. So in the end, Jeremy does compare the speeds, and the backward pass is slightly slower. Down below, we do call the PyTorch library, and the backward pass was twice as slow. The reason mentioned was we are computing all of the gradients, and maybe PyTorch isn't computing all of the gradients. I did skip over another refactoring portion. So we do refactor further where these neat exceptions are defined. So we really want to ensure that whenever you import module, which is our replica of nn.module, that you have to define your own forward pass. You need to override this in terms of OOP terms. If you do not, these few exceptions will be raised. We again refine the functions from earlier, and then we finally get to the PyTorch like API. And when Jeremy does compare this, it's as fast as PyTorch. And the backward pass, like I mentioned, is twice as slow due to the, maybe because we're computing all of the gradients. That's all for the lesson walkthrough. Any questions from the lecture notebook?
I had one question. During the lecture, Jeremy had said something about convolutional math, about going forward is multiplying it with a weight matrix, and backdrop is, I think, taking the transpose of the weight matrix. Do you recall that part? I think it cited some article by Matthew Klein-Smith. I don't remember the name.
I think
choosing fan out is a
Yeah.
mode.
Yeah, that part. Will you just explain that part again, the fan out one?
Okay. So how these chiming normalizations are computed with this formula is you need to divide by the square root of your input size. And when you're doing the forward pass, these will be different from when you're doing the backward pass. So just to tell PyTorch that you're in your forward pass, or if you're in your backward pass, you need to define the mode as fan out. So when your fan is throwing the air outside, that's how I sort of remembered it, is when you're throwing air outside is when you're doing forward pass, and when it's coming back to you is when you change it to fan in is when you're doing the backward pass.
That's a good analogy.
If I recall correctly, basically Fanin is a number of input that is coming to activation that neuron, and fan out is the number of output going out of that neuron. So what happened? You can have this installation with respect to the number of Fanin. I mean, how many neurons are coming when you're going in a forward pass, and in the backward you can say the number of output that was going from the neuron. But what happened in PyTorch is they don't save the matrix the way we are saving. So they are using a transpose of the matrix. So that's the reason he shows the shape of that weight matrix. It was a transpose. So since we want to use the input number of input of a weight matrix, so we said to the PyTorch use a fan out because you are using the transpose of a matrix as the weight matrix. Did you get my point? No, okay. So if you see the shape here, one is showing 50,784, and if you go top, little bit top, yeah. So the way we are saving is 784 by 50, right? But the PyTorch is saving is, yes. So the PyTorch save is 50,784, and the way we want is 784,50. So we want as the input as 784, and so that's it. We are saying to PyTorch use fan out, means the 784.
Okay.
Got it. Any other questions? So thankfully I'm on time for the mini presentations. But if you have any questions from the lecture notebook.
Yes, so the last thing is that I can echo from the chat that pretty much everyone says that you did a great job, Sanyam.
Thank you. I was worried because I was rushing through this, but if you really want to understand the class definitions, in my experience, please do replicate them. They're really helpful. Can I proceed furthermore? I want to give a discussion of the sequence to sequence paper. Philip and Robert, is it okay if I quickly finish my mini presentation first?
Yes, sure, go ahead.
Yeah, definitely.
So the paper is this classic paper called Sequence to Sequence Learning with Neural Networks. I've been doing this 5-minute paper series. So this was one of the classic papers in the sense that this really showcased to the world that neural networks can be used for language translation. And this is from 2014, so many of the definitions were still sort of funny that deep learning has only shown promise in some areas, which if you're going through the paper might seem funny in 2019. But this was one of the pioneer papers, and for the discussions that I have planned next week, I'll be building up on machine translation. So that's why I wanted to cover this paper for this week. To give you a quick TLDR, during the time neural nets only worked with fixed length inputs, which was the problem being dealt with translation, that you do not have a fixed length input. So the authors dealt with it by using two LSTM architectures, which are now known as encoder-decoder in most of the scenarios. And their target language was from English to French. And to again highlight that during the point of writing this paper, statistical machine learning translation was the current state of the art back then. And this paper showed the promise of neural machine translation. So the crux of paper is to use two LSTMs. They use a 4-layer deep LSTM network. The first LSTM essentially maps your input into a fixed size tensor, which is then decoded. And these are not the terms from the paper. These are my own addition in the article. These fixed representations are then mapped to your output is how the translation happens. So using these two-layer LSTM encoder-decoder architecture is really what allowed translation when they did not have the technology to support varying length inputs. How the model works in essence is you feed in all of your input and of string character, EOS character, then the output generation starts. We're trying to generate the, sorry, I'll mute all of the participants.
Sorry, I'm not logged in as TWiML, so I can't mute everyone.
I'll have to stop sharing, I think. Oh, no problem.
Yeah.
I have muted everyone. If you want to speak, please, and feel free to unmute yourself. So what we're trying to predict is the conditional probability given the input statements. And note that the length of y is represented as t dash and x is t. So these are really of different lengths. For example, a word in English may map into 2 or 3 words in French. So it does make sense. And this was really a challenge, and no other papers at that time had tried to do this different length mapping. The model has 2 LSTMs, as I had mentioned. The deep LSTM has 4 layers in it in 2014. And a trick that was highly spoken of was this model image is sort of false because the authors found that reversing the input really helped them improve the accuracy further. So the explanation to that, incomplete explanation to that was, if we pass in CBA as the input, so as opposed to passing ABC sequentially when we're trying to predict WXYZ, if we pass it in as CBA, that minimizes something known as quote-unquote time lag between A and W, the targets, while maintaining the same average time lag as the original sequence. So reversing the sequence really helped SGD perform better.
Sanyam, there is a question from DC in the chat, and he wants to know why reserving the order of the input helped performance so much. Is it because they wait to predict the EOS?
You mentioned reversing the order, right?
Yeah, reversing.
Okay,
DC,
so
maybe you can unmute yourself and jump in.
I think your computer audio is not connected, so if you
Okay.
can.
Okay.
Sorry, I had it on mute on my phone
Okay.
and the computer. I just didn't quite understand. It said one of the biggest things that they discovered was that reversing the order of the input really helped the performance, and I didn't quite understand why.
So as I mentioned, it minimizes the time lag between, that's what they call it, between your input and target. So you want to predict W using A, right? And if that is passed earlier, your neural net has some time lag to it, opposed to you passing it in inverse order. So that minimizes the lag between A and C. But since you just reverse the sentence, the average of it remains the same.
Okay, that totally makes sense. Thanks.
Sure thing. So a few more details. They created a vocab out of the 160,000 most frequent words and 80,000 of the most frequent words for the target language. Every other thing was marked as UNC. As we know it from Fast.ai library, it does the same. And what we're trying to maximize is the log probability. The translations are produced using argmax, which produces the most probable outcomes. And what they call hypotheses are the pairs of sentences that are generated for each input sentence. This is done using a beam search. So if you're not from CS background, beam search basically searches for similar phrases in this context. So there's this problem with RNNs that if you keep predicting the most probable word as the next word, it might get stuck in a loop. So for those reasons also you would want to do a beam search. And this stops when you read the end of statement character because you just wanted to predict a sentence. So I assume this is a sentence to sentence translation. Since we've discussed a lot of initialization today, these are initialized using the following distribution, a uniform distribution between these values. I assume it's from experimentation. To deal with exploding gradients, they scale the gradients as follows. So they divide it by a fixed number after a fixed number of layers, or fixed number for each patch. I apologize, they divided for each patch with the following numbers. And their best result was something that calculus might be familiar with, was an ensemble of 5 reversed LS Theorems that they call it, with a beam search size of 12. So search size would, I believe, mention like how many words are you searching at a moment. So you're searching for 12 possible next words while predicting each next word in the sequence. And to the author's surprise, this is now sort of our basic assumption, but even at that time, the authors were really surprised that these did really well on translations. I do not speak French, so I took the author's word for it, but this was something that they did not expect the model to do really well upon. And they did a quick PCA analysis of if the translations change the meaning a lot. Based on the graph, it did not. And to finally conclude, this is an important paper to the NLP community, I would say, because this really created this field of neural machine translation, and something that almost all of the libraries now call as an encoder decoder was first introduced here. And to the author's surprise, this also created or allowed us to translate long sentences. And if you actually go through the paper, I was really surprised that they had also mentioned the details of parallelizing the code across 8 machines using C++ code, which is when I realized that in 2014, TensorFlow was not available to the public, even though this paper is from Google, but I'm not sure if they internally used TensorFlow at that point. So that was, again, an interesting aspect of the paper, that they do go into a lot of depth of how the implementation is done in C++ and how the matrices are stored in memory. That's all for my presentation. Any questions from this paper?
Yeah, could you talk a little bit more about the results? I didn't totally understand because of the representation. They used the blue score and state of the art. Like, can you just talk a little bit more about what it means, and like, did they break a major benchmark?
They did get the best state of the art after doing ensemble, so it was not a straightforward model. I'm not sure with the exact definition of blue score, but it's how you evaluate translations, if I remember correctly. And using these few tricks along with the original process, they did beat the then state of the art. And but again, for the other benchmark for the test, I think the test set is called NTST14 and WMT14. They had to rescore the baseline with a few more tricks, which eventually led them to beat the benchmark. Those are 2 mathy details for a 5-minute discussion, which is why I skipped over them.
No, that was perfect. I've got it better. I just wasn't sure if the Oracle rescoring at the bottom was them or, but yeah, I understand better now. Thank you.
I'm not sure either now, but I'll sort of double check and let everyone know in the Slack channel.
Yeah,
So
I just like to add one thing. I just gone through one of Jeremy's videos of Fast.ai version 2 last year, and I think in lesson 11 he had captured, he had done the sequence to sequence model of English to French. Here, actually, his opinion of the blue score was that it's a very horrible metric, but it's something that's just used, so he just used it. His main thing was just base it on practical translations. For him, that was a better score. So blue score, I think, is something just for paper sake.
But how do we evaluate the other option? Does a human check the sentences manually?
That was what his opinion was. I think he checked it through Google Translate.
Okay.
Yeah.
That was again mentioned in this paper that the long translation, the long length sentence translation can be verified through Google Translate. So even I think the authors were somewhat aligned with that opinion.
I had kind of maybe a stupid question, but so the way that I understand this, right, is you're taking some document or some query and you're basically embedding it into like a vector space, right? And so I know with like Word2Vec and Glove that you're taking each word and you're representing that in a vector space. And is the biggest kind of advancement here that you're using like the LSTM kind of structure to make that vector space relative to the sequence of words that are happening, and that's why it works so well with translation?
That's right. Okay, so I'll stop sharing and we can move on to the next mini presentation.
Sanyam, can you take over the chat? I have to leave now.
No problem.
So see you all next week.
We have two presentations next. So maybe Robert, do you want to start with yours?
Yeah, since it's my first time, I'll probably need, like, how do I share my screen?
If you hover your mouse in the UI, you'll see the share option, and then you'll have to select the window that you need to share.
Okay, pretty sure it's that one. Can you guys see?
Yep.
Okay, cool. So yeah, I wanted to talk about something that I found really helpful in this past week, which was the built-in parallel function in Fast.ai. It comes from kind of semi-real world problem I had. So I'll go through the notebook here. Here is if I can get in the chat, a quick link to the blog if you guys want to follow along. And then I've also got a notebook up for playing around and kind of exploring the functions on GitHub in a small repo there. So yeah, this is all just basic imports, stuff I need to generate spectrograms. So I was competing in the Google TensorFlow speech challenge for audio recognition, and it's an expired competition, but one of the things it requires is judging and predicting on huge amounts of audio. And so I ran into the problem that right here, I had 158,000 files in my test set, and my method was based on generating spectrograms. So taking a audio file and converting it to an image for image classification. And, I did a few of them on the test set. My training set was much smaller, and I calculated it was going to take me 13 hours to generate my test set spectrograms for only, one set of settings. You can parameterize it a bunch of different ways. So I went looking for answers, and I'm definitely not an expert coder. I haven't spent too much time in the Fast.ai code base. So I wasn't really comfortable with writing my own multi-processing and threading. It was pretty intimidating. But I came across rewatching lecture 7 of part 1 with Jeremy. He mentions that Fast.ai has a built-in parallel function, which is really helpful. For me, it cut things down about 3x in terms of time. But it does have a few quirks. I talked to Sylvain about it a bit, and he says that it's kind of meant as an internal convenience function for them. So I'd really want to go over and show people how to use it and kind of how to understand what's going on, because it does have some weird quirks. So if we check out the docs here, you can see parallel. It takes a function, takes a collection, and calls the function on every element of the collection in parallel for you. So it seems really simple. You know, you just chuck in your function and the arguments to that function you want to run. You know, maybe you have a list of 1,000 things you want to pass to your function one at a time. It'll run them in parallel, handle multiprocessing, and you don't have to worry about it. So there are a few things though. Your function can only take one argument, which is a bit tricky if you have, you know, most functions we write often take 3 things. So I'll go into a specific example. This is just some basic code to generate a spectrogram. It takes a file name, a source path, and a destination path, and it'll load in the WAV file, convert it to a spectrogram, and save it for me. So let's go over how to use this if this were your function, how to convert it to work with parallel. So the only problem is our function genspec takes 3 arguments and parallel is expecting a function that takes 1. There are a few ways around this. It depends on your particular function. If the additional arguments are fixed and static, you can make a new function with either default values, or you can use Python's partial to create a function that fits Parallel's model, accepting only 1 argument. So I'll go into detail on that. We can create a partial. Since our source path and destination path in this case are always the same, we can create a partial, which for those who don't know, it's just a Python function that allows you to make a new function by passing some constant arguments in to an existing function. So we go from having genspec, which takes 3 arguments, to this partial, which will only take 1, which is the specific file name, the thing that changes each time. And we can go ahead and run it here, and an interesting thing happens. Up here, I benchmarked it, I believe, yeah, without running parallel, just my normal method, and it took 30 seconds for 100 spectrograms. So again, at that rate, it would be 13.16 hours. And if you come down here, the progress bar completes. It's super, I may have overwritten. Oh yeah, here we go. Yeah, 466 milliseconds. Earlier when I ran it, it was 196 milliseconds, down from 30 seconds. So 150x faster. In this case, about 75 times faster. Doesn't seem possible, so we do a sanity check, and in our spectrogram path, nothing was created, nothing showed up. So this is kind of a flaw in the way Parallel is implemented. Like, the documentation makes it look like you can just pass in any function and its arguments and it'll run, but it actually fails silently. And if you pull up the full documentation, which I've got here, you can see why. And if anyone has any questions, I feel like I'm jumping around a lot, just stop me at any time. So again, here's the full documentation taken from Fast.ai docs. And it will call function on every element of array in Parallel using max workers. That we already knew. But it says function must accept both the value and index of each array argument. So it means that your function, as you can see here, not only must take that 1 argument, but must just take an arbitrary index that it doesn't use. And yeah, I talk about it a bit down here. Func must accept both the value and index of each array element. So the function you pass in needs to be of a special type. It needs to accept 2 arguments. 1 is whatever it needs to do its work. So basically your argument, and then 1 is this special index that comes from array. And I talked to Sylvain about it, and he said that the index is required to make verify images work. If you guys remember the widget from lesson 1 or 2 of part 1, that lets you go through and make sure all your images are correctly loading from Google. He said that Parallel is meant to be a convenience function for internal use. So if you're more advanced, you can implement your own version using process pool executor, which is actually surprisingly easy. So in order to make this work, what you have to do is make a function that will be of the format needed. So we rewrite our function to accept this index. And again, this is totally useless. We don't do anything with it. I believe we could even get away with just putting that symbol in there. But for notation's sake, I'll keep it there. And then we go back, recreate our partial, this time passing in this genspec parallel function, filling in the source path to be the constant, destination path to be the constant. And we run it. This time it works. It looks like it took 10.7 seconds. Our original was around 30. I'll repeat the sanity check, and there are indeed 100 files there. So we're already 3 times faster. That's going to cut down my processing time from 13.16 to 4.5 hours. And you get a progress bar. It's really annoying when you run something that's going to take 13 hours and you don't have a progress bar. So that's pretty much all you need to know to use it. And I feel like I ran over that kind of fast. So, you know, grabbing the notebook or checking out the blog where I had more of a toy example, I think I did generating square numbers. These functions are a lot simpler. I think the concepts are a lot more clear. But I'll stop there. Does anyone have any questions?
Could you go over like exactly what a partial is one more time?
Yeah, absolutely. So a partial is, let me see. I don't think you can get, no, you can't get dot partial on here. A partial is something I was first introduced to in part 1 of Fast.ai. So I don't have a ton of experience with it, but what it essentially does is fills in arguments to your function. So let's say we have a function that takes 2 numbers and multiplies them together. Define mul x comma y, return, let's just do print to make it a little easier, x times y. There you go. And then let's say that we decide we want to have a special function to multiply just by 4. And we want to do it multiplying by 4 every time. So define 4 times x. And what we can do is, instead of rewriting our function, we can just build off of mult that we already have it. 4 times x, 4 times equals partial. Mult comma, I think mult comma 4 should work. And then we can do, someone stop me here if this is wrong, but you can do 4 times 12, we get 48. So essentially what you're doing is just kind of passing a permanent argument into a function. That way, if you don't want to rewrite the whole thing. So for me, like, I could have taken this big genspec thing and just made genspec parallel that has source path defined as a constant and destination path as a constant. But then I've got this big chunk of code that is just duplicated for no reason. So a partial is just a convenient way to do that.
Hey, Robert, I have a question. So the limitation that the function only accepts 1 argument, is that, can you just get around that by giving it a list of all the arguments that you want? Just passing in a single argument that is a list of 2 arguments or 3 arguments?
Yeah, great question. And that's what you end up doing. So I'll actually use that to kind of transition into the second case, which is what do you do when you have a function that takes 3 arguments and they aren't constant? They can all be variable. We need all 3 of them. And the answer is to pack them into a tuple together and make a version of your argument that takes, a version of your function that takes that tuple, unpacks it, and then runs your code. It's, pretty inconvenient, but
I assume that could be done using star args or star KW args.
Yes, star args.
So I had trouble getting that to work specifically because of the presence of the index function. Because again, you have to, sorry, not the index function, the index variable that gets passed in, because it requires us to accept this index. Because I thought, yeah, so then you have to have and index needs to be your second argument. So you can't do something like star args, comma. Maybe you can. I would definitely recommend playing around with it yourselves and trying to get it to work, because it did seem like a good point for it. But I remember having issues with it and thinking it wasn't kind of the optimal way to handle things. But jumping into the tuple solution is pretty easy. So I did try doing it with a Lambda first, which is what someone suggested in the developer chat. And I kind of stumbled upon an interesting thing I'll share. For those who don't know, a Lambda is just an anonymous one-line function in Python. You can just make it up on the fly and it doesn't get stored. So you can see here, function Lambda X. That means function with one variable X. Take X and do this to it. And I'm saving that as a function. Anyway, if you do that and you run it once, it works. But if you try and run it in parallel, what happens is that Fast.ai's parallel somewhere down the line in the source code calls pickle, which will break everything, because you can't pickle lambdas easily in Python. So that was just a random interesting thing that I didn't know. The genspec tuple is really simple. You take a kind of argument that's a tuple, you unpack it here into your things, and then you call your original. And then you can pass it to parallel along with a list of tuples containing your arguments. So I have one of those. I think I'm running short on time, but it is somewhere in here generated. But I'll share the notebook, and people who are interested can go through in more detail. And like I said, there's more toy examples in the blog. I found it to be about 3x faster. The last thing I'll breeze through really quickly is what if you need to store return values. And I really recommend going through this if you're not that comfortable playing with the Fast.ai code base, because to me it looks really intimidating, but every time I end up copying a function out or playing around with it, it's really, really accessible. Like this source code here at the top of the page looks like gibberish to me until I break it down line by line, and then I see that it's mostly just syntax, and it's actually really quite simple. So what I found was that I could copy in and make my parallel function and alter it however I wanted. I got rid of the index that was annoying me. I had some return values so I could return a list in case I needed to get the stuff out, because when it's in Fast.ai's library, there's no way for you to return the values. You're kind of reliant on what they intended it to do. But if you implement it yourself, which is as simple as copying the code in, changing a line or two, it works great. You can return values. You can change. You can say, I don't like the index. And so any questions on that?
There are no questions from the chat. Thanks for the great presentation and some live coding. There are two comments from Suayu. So he mentions partial is like bind in C++. It binds default values to a subset of arguments of the original function. And there's also this mention of this library called Dask, which I assume helps in parallelization.
Okay, yeah, and that's something that I kind of want to do a potential follow-up a couple weeks down the line, because there are tons of different multi-threading and processing libraries in Python. So there might be a better implementation out there. If anyone is good with this type of stuff, feel free to pick it up where I leave off here, because I think like this is really important, because it's, you know, cutting down hours off people's coding time if they're doing this on like a local CPU for image pre-processing. So I think there's a lot of value to be gained there by exploring the topic.
I know we're short on time for Philip, but to give others more context, so this was to help with your TensorFlow challenge on Kaggle, which I believe had a lot of spectrograms.
Yeah.
And since I know you rent a server, you'd want to minimize the time that you're paying for, which is where this would really help.
Yeah, definitely that as well, because I'm pretty new to Fast.ai. I started maybe 7 weeks ago, and I've had some trouble getting a local install of Fast.ai. So I'm forced to, if I want to use something like Parallel, that's from the Fast.ai library, I have to use, pay for my server, which is pretty wasteful for CPU operations.
I assume this will also be very helpful. Like once you have it figured out, how do you parallelize your required pre-processing? You can fire up a AWS instance with many more cores and just have it finish in an hour. Since especially when you're participating in a live Kaggle competition, you really want to experiment as fast as possible.
Definitely, yeah. And we talked about that earlier. I think it's a great idea to be like, having different machines for different purposes, having a CPU machine that just maxes that out and saves you the time. Like you said, it comes out cheaper in the end. So
otherwise, you
that's
just
a good
end up
tip.
getting a single GPU server, which is not really what you're using here.
Exactly.
Okay, thanks for the great presentation. I think we have 8 minutes remaining for Philip. So, Philip, do you want to do the presentation today, or do you want to move it?
Yeah,
to
sure. I can do it. I have to do it quick and fast now. I wanted to thank Rob. It was very interesting, and I think it's useful. So thank you. And since we don't have much time,
Rob, you'll have to stop sharing your screen so that Philip can start.
I will just start sharing my screen. Okay. 1, 2, 3, 4, 5. How do I share my screen, or did people already get me?
Just select the portion that you want to share.
Okay, here, yes. Okay. Can people see the presentation?
Not yet. Nope. Can you try stop sharing and start sharing again?
Wait a second. Okay. Can people now see it?
Yeah, we can see it.
Yes, sir.
Okay. So the topic is interpretable deep learning in drug discovery. There was this paper that I shared on the Slack channel by Hochreiter et al. It's going to be published in a book on interpretable AI. It's as you know, very sorry, I have to speed up now a little bit. It's going to be a little bit fast. It's part of a book that's going to be published on interpretable AI. It's of course a very in discussion topic right now, or a very hot topic, let's say. Let's see how we can apply this now to basically drug discovery. Okay, this is the case not only in this application area of pharmacology, but everywhere. Like without a means of interpretation, neural networks, you all know this, that they are basically can be black boxes, because it's not really understandable for a human being what they really do or what they mean. And especially in this context, where we want to predict essentially toxicities, or want to predict is a molecule, is a drug, is basically toxic, or is it not toxic? Especially there, you would want to have some interpretability, especially since you could implement these systems as sort of recommender systems or decision support systems for human experts. And these human experts then are, of course, pharmacologists or medicinal chemists, and they definitely don't trust black boxes. And I can certainly understand why. I would do exactly the same thing, especially with this high stakes that are here, here. Okay. But so, as we will see, as Hochreiter et al. Did, you can essentially, when you have a data set, and we will discuss the massive data sets that they used for this, you have essentially molecular structures, and you essentially, by the way, the chat is going crazy. I don't know.
I'm keeping an eye on it.
A little bit interrupting to me, or annoying, and not to say annoying, but yeah, okay. So. Yeah, essentially you have data sets that give you the structural formula of these molecules, and then they tell you they're toxic or not toxic, basically. Okay, So, and then there are, in chemistry, there are basically structures that are called pharmacophores. These are just structures and molecules that are pharmacologically active, like certain functional groups that you could have, for example, an alcohol group, and then a subgroup of these pharmacophores are toxicophores. These are structures that are then obviously you can etymologically derive it that these are pharmacophores that are just toxic. The goal of drug discovery is very easy. It's essentially if you want to find molecules that cure diseases and nourish human health in the broadest possible sense. And obviously, when you're a big pharmaceutical company, you have to screen large amounts of molecules that are then not used, actually, that are then thrown away into the garbage, essentially. And that's what we refer to as high throughput screening. And high throughput screening just means that you have automated robots that test thousands and thousands of molecules that could be potentially could potentially be a drug, used as a drug. And obviously this nowadays has a rather long history in drug discovery. And if we want to essentially predict the outcomes, we use deep learning essentially, because it turned out that deep neural nets are actually applicable in this area and perform very good in terms of predicting these physical experiments, such that we don't have to do the physical experiment and can essentially save time and cost. This is a high throughput robot that you can see here, just so that you can see it, that this is really high tech and yeah, high throughput screening. That's how you would do it in a physical sense when you were to physically implement a high throughput screening. Now there's even deep learning nowadays, or I've read in the literature that they can even do automated molecule generation or propose molecules. These are then I would now, this is not literature knowledge, but I would guess that then these are then basically GANs that you would that can do that. And as we've said, you know, if you have interpretable neural nets that not only predict you with a high accuracy if a molecule is toxic or not, but it could also sort of say why it thinks it's toxic, and could even show to the human expert functional groups for why it would be toxic. That would be really nice. Now, there are two types they used in the paper: descriptor-based feed-forward neural networks and graph convolutional neural networks. With the latter, I think they mentioned the advantage is that you can essentially, they can figure out the molecular representation themselves, whereas with descriptor-based feed-forward neural networks, you essentially have as input vector something that we will see. I have to go to the next slide, and because we have to talk about how can you describe a molecule. It brings us into the area of molecular representation. How do you define these small molecules? You can have a molecular formula, you can have a structural formula. You know this probably from chemistry. And you can even have with proteins, let's get into that, but you can have three-dimensional structures. The conformation also plays a role. And you can also have combinations of the three above, which then makes it really complicated and complex. And here we see a three-dimensional structure, a model of such a molecule. And yeah. This we don't have to go over. Essentially, what they then did, they tested their model on an alcohol toy set where they just had 20,147 samples, including 1,236 positives, and positives was just defined as basically has an alcohol group. Don't get me started on the chemistry or not in it, and these so-called ECFPs are then used. This is a short notation or description for basically you describe a molecule sort of in your database as a ground state, and then you just describe do you have certain functional groups on it. And yeah, that's what you then feed into the system. And then they found that the area under the curve was bigger than 0.99, which is of course quite nice. And so they were very pleased with that. But then they checked, can we really get interpretations for the human expert? And here you can see how good it essentially is, because the red areas show you why it decided for the positive samples, and you can essentially see that it perfectly picked up the alcohol structure that a human expert would pick up. And that gave them confidence that this was, of course, a toy example that they sort of used as a spike in, and then they let these systems onto the TOX 21 challenge data set, which is it's a rather huge data set containing thousands of examples of molecules that are basically toxic or not toxic. And they let their systems on it, and of course got a nice area under the curve. And they even mentioned, I think it was in the top 10 of this competition already, without the interpretability. And here you can see, okay, the system sort of picked up, can sort of pick up what the human expert would pick up. Now, I'm not a pharmacologist, I'm not an expert on it, but the functional groups that are toxic got picked up.
Hey, Philip, I have a question. Yes, could you say something about the input format? What information was provided in the training data?
You have to imagine it like that. You have essentially a database, and I'm not so 100% sure what I think the input data is that you can essentially have like I said, a ground state, and then you have just, I think it's, for example, if you have an OH group, then it's just a zero. A 1 in this case, if you have one. Or if you have, let's say, a COOH group, then you have a 1. Or if you have an NO group, then you have a 1. So that's and these things then get learned, and that's how what I understand, I should mention, or how I think it worked. It then shows you this is important, this functional group is important, and puts it out to you. Does that make sense?
Yeah, I'm just wondering how, because it seems like an easy problem, a quote unquote easy problem. If I don't know, I'm not a chemist, and I know nothing about this, but I mean, alcohol probably is formed of a certain number of COOH groups, a certain number of OH groups, and so on. So it would seem like an easy problem to say, oh, this training example has all the components of an alcohol, so let's label it alcohol. It seems just offhand, it seems like an easy problem.
Yeah, sure. It's definitely the case. I have to rush a little bit through I'm not aware. Maybe Sanyam can tell me the time to rush a little bit through it.
We're 5 minutes over the limit, but
shit. Sorry. So here you can basically see then that their system sort of work, because essentially on the left side you can see the structure example, on the right side you can see sort of the interpretability or the structures that it picked up in the data set. And yeah, this brings me to the end. The conclusion for me was use interpretable deep learning. Of course, it's better, but that's kind of a tautology, especially in this area. So thanks for the attention and have a great weekend. Any questions regarding this? I don't want to take time away from your well-deserved weekend.
No questions from the chat.
No questions?
If you could please share the link to the presentation, maybe after.
Yeah, sure. I will share it in the Slack channel. That would probably be best.
Also, Rob, there are questions. If you could share the notebook in the Slack channel, that'll be great. So before we conclude, thanks for the great mini presentations, and we'll see you next week for the 9th, I assume it's 9th lecture discussion. And if anyone wants to do any further mini discussions, please feel free to reach out to me or anyone from the hosting team.